Welcome back to the first session of the afternoon. And I hope you all had nice lunch and also maybe a coffee to help you keep awake. So in this session, we will have two talks, 45 minutes talk. First talk will be given by Suvodip Mukherjee and second will be by Wang Lee Park. So we will start with the Suvodip talk, and it will not be a continuation, but on a different topic which Suvodip talked about yesterday. Over to you, Suvodip.
Great, thanks a lot. Yeah, so I'm going to switch gear completely. I'm going to talk about two different frequency bands of gravitational waves. So as the organizers asked, the first part was more like a pedagogical talk to give you an introduction to the physics of cosmic microwave background, which can be used to understand or discover gravitational waves. Of course, ask me questions. When you're asking me questions, you can ask me questions from the yesterday's talk as well. Today, what I'm going to cover mainly is about what, on the stochastic background side, our latest developments going on in both LIGO and in the nano-hertz gravitational wave signal. Okay. So, to bring this particular topic in the cosmological or astrophysical context, what I would like to just tell you that this has been fabulous years of measuring the cosmic history from very low redshift up to very high redshift universe through several electromagnetic observations, and this has been really great. But this doesn't mean we have really learned a lot about certain epochs in the universe, particularly at the high redshift. The high redshift universe remains to be quite unknown to us, to an extent that you can possibly start seeing that JWST observations are now revealing very much new about galaxy properties. And you have heard so many talks that as you go up to even higher redshifts and beyond cosmic microwave background, there's a lot of physics which we can deal with and of cosmological origin. So both cosmological and astrophysical sources are going to be an extremely important aspect which we can probe using really the stellar graveyards. What I would like to say that using gravitational wave sources of astrophysical origin and trying to disentangling it from the cosmological one, the low redshift piece, the mid redshift piece, and the high redshift piece, this is going to be really exciting with the measurements of gravitational waves. What's pretty new now, if I like to bring this previous picture into the context in terms of black holes and gravitational waves. So this is my cosmic history. This is the mass range over which several black holes form. This is the cosmic time arrow. And this is the gravitational wave frequencies. This is the band which we detect from LIGO, Virgo, Kagra, currently primarily LIGO and Virgo, which is operational. Kagra is in the engineering runs. LISA is not yet operational, will be operational by next decade. Pulsar timing array is already operational. You have already heard talk on this. What's very interesting is that this entire range, when I put this diagram, basically I can explore the entire cosmic history using gravitational wave sources in these different bands. And I am going to now particularly focus on a couple of areas on where we are making some data-driven inferences in the frontier of gravitational waves. I'll start with LIGO Virgo Kagra band, which is the Hecto-hertz band, and I'll slowly move here to the nano-hertz band. That's the plan. Okay. Of course, events played a major role, individual events. We have 90 of them until GWTC3, and as we speak, we are seeing more sources. But this conference is all about stochastic background, right? So I'm going to focus only on the backgrounds part or the high redshift universe. To give you a 101 about the stochastic gravitational wave background of astrophysical origin, but I'd like to tell you that in simple word, what it means that if I see binary black holes up to some detector horizon or distance or redshift, anything which are far away, I don't see as an individual event. I cannot detect it with a, say, a match filtering SNR of 8 or so. So anything far away starts contributing to my stochastic gravitational wave background. So if they are more in number or they are less in number, depending upon that, this quantity will change, which is the amount of energy each source deposits times how many of them are there. This integration with respect to the critical energy density of the universe gives me the omega GW background, or what we call the power spectrum. I would like to measure this quantity as a function of frequency, and if I can do so, this is an excellent probe to anything far away in the universe, right? It's a high redshift probe to the universe. That's why I'm saying I would like to measure the background as a function of redshift and up to high redshift universe. So what's really new and what's really completely unknown to us, if I have to put it, ask you what are the key scientific questions we have. One of the key scientific questions which I've heard already a couple of times in this particular meeting, that if I give you a pair of black holes, is there a unique way to tell whether they're astrophysical or primordial? What are the key signatures that I would like to use? Possibly first thing we would like to ask, okay, if they're astrophysical, what is the astrophysical signature of these black holes? So the astrophysical black holes means black holes formed from stars, so possibly they are going to follow the distribution of star in the universe. The merger rate is going to be connected with the astrophysical stellar distribution. This is the star formation rate history. Another important aspect is that black holes of all masses don't form astrophysically. Like it's a very famous bound from the low mass end. We know that below 1.4 solar mass we call it, we do not call it a black hole, do not call it a start talking about neutron star. And when we start going to higher and higher masses, we are not sure what to really call a black hole. Well-known problem. Is there a lower mass gap? Is there a mass gap at all? We don't know. Similar story is there also in the higher masses. Black holes of very high masses also don't form because of some physical effects called pair instability supernova. If the stars are pretty big, they can actually throw away all their material through oscillations during the pair instability supernova. And this is a very well-known work by Robert Farmer showing that depending on the core masses and the black hole mass, you typically start forming black hole up to some masses. You see, I do not see black holes beyond some 50 or 60 solar mass. Of course, this number is going to vary with different assumptions was made in this, but from data, we can possibly infer this directly if there's a way out. And what it really depends on, it depends on the stellar metallicity, a very important aspect. The metallicity of the universe is more at low redshift because a lot of stars has formed. Those stars has polluted the interstellar medium during supernova explosion. So I have metals, and then when the new stars are forming from those, they are metal heavy. But if I go to high redshift, I expect to see black holes or stars has less metals. As a result, the corresponding black holes I would be expecting to see are going to be heavier. So now my question comes is that if we observe that is redshifted mass, which is the 1 plus z times the true masses, and I have a way to go in this arrow of redshift, how do I really measure them? What do I really measure them? I measure a quantity of how many of them are there as a function of redshift and how heavy are they. This is a place where things start becoming a bit confusing. I would like to understand the astrophysical or primordial origin of black holes. To know, for me to do that, I have to tell you, are there more black holes or less black holes at high redshift? Or are there black holes of very heavier masses? Because of these are the two nice observable quantity that I have. So that means I would like to now capture these objects, whether they are more or less in number as I proceed, and that directly starts depending upon which quantity? The merger rate of sources. So here I am showing you a plot on merger rate of sources. This possibly will be covered in a later part of the talk in this meeting as well. For astrophysical black holes, which follows the underlying stellar distributions, and primordial black holes, which is over here by these dotted lines. You can possibly start seeing over here, up to redshift 0.112, up to over here, things are almost very same. But there is a peak in the star formation rate. Star formation rate is typically peaks around redshift of 1.9. That means if I suppose go to redshift 2, 3, 4, and I ask the question, what is the shape of this merger rate of binary sources? The shape of the merger rate of binary sources that is a very direct tracer of whether it's an object of astrophysical origin or primordial origin. Because if you start seeing a lot of black holes before forming the stars, it is very difficult to argue that they are coming from astrophysical origin. So if I now would like to draw this coordinate system where I can measure or I can distinguish astrophysical black holes from primordial black holes, I say in the redshift range above 2, if I see sources at much higher masses with a rate which is following one of these distributions, it's a very interesting signature for me to distinguish between astrophysical black holes and primordial black holes. Whereas if I go to the lower mass end and I see even at high redshift or low redshift, low mass end is pretty cleaner probe to look for primordial black holes because we do not have a way to make astrophysical black holes there easily. In this observable plane, these are the places where I get a yes answer to probe this aspect, and these are the places I'm not sure about. It's not a great distinguisher between astrophysical sources and primordial black holes. And what is interesting is if I now would like to plot what of these aspects will actually measure from the current / future gravitational detectors. So these are the regions where I will be measuring sources individually, okay? From Advanced LIGO, Einstein Telescope, Cosmic Explorer. And anything which are not in these regions or these regions are basically not detected. And as I told you, if I don't detect them as individual events, they contribute to my stochastic gravitational background. So entire these two pieces, high redshift, are in the bucket of an observable quantity of stochastic gravitational background to explore the high redshift universe properties and distinguish it from astrophysical and primordial. That's a very important signature. So let's ask, what is the signature? So if you now calculate for different mass distribution of primordial black holes, astrophysical black holes, and their merger rates, what's the two important signature is that if I have a top heavy black hole mass distribution, means more black holes of higher masses, that will be contributing more at a lower frequency, because heavier black holes only contributes mainly at a lower frequency. I start getting a shape of the omega GW power spectrum as a function of frequency, which is a little bit red, means more power at low frequency than high frequency. But if they are typical of astrophysical distribution, which is bottom heavy, there are more objects at lower mass end, around 5-ish solar mass and so on, what you have seen from the LIGO Virgo Kagura, they will typically show you a bluish spectrum, means more power at a higher frequency. That's a very interesting distinguishing feature on omega GW background that one can measure for different fraction of delay time distributions, means how delayed are black hole mergers from the star formation rate for different mass distributions and so on. Now, using this avenue, we have obtained the very first constraints on the primordial black hole mass rate and distribution from GW from third catalog. So this is the stochastic background data from the third observation run of LIGO Virgo Kagura. Our current bounds are pretty weak. You can clearly see that we haven't made a measurement of the stochastic background yet. So what it basically tells you that we have a cutoff, means very high power law increase is ruled out. Means if there are the steep increase in the merger rate, that we do not see from data. Why? Because then you should have a very loud stochastic gravitational background. And we have some very weak constraints on other parameters, but this is the main parameter which starts getting constrained from the current data. But this is not very promising at this stage because of the sensitivity. But if you move to the next with A+, you can start now asking the question, how well can I measure the power law increase in the merger rate? That's a very neat signature, right? One thing comes down if it is astrophysical, other thing is always increasing function. So can I measure this increasing aspect of the merger rate, and that is captured by this alpha parameter, and the fraction of primordial black holes with respect to astrophysical black holes. Remember, it is not primordial black holes with respect to dark matter. I do not know whether they are dark matter or not. I'm asking, out of all the black holes I have seen, what fraction of them follows a certain mass distribution and merger rate distribution. And these are the two quantities which you can start measuring pretty well from the, not I would say to an extent where we can rule out some of the situations of very low alphas, but definitely very high alphas are very strongly constrained. This is something means that in O5-ish A+ era, LIGO, Virgo, Kagra detectors, even non-detection of stochastic gravitational wave background will already start putting very interesting constraints on the primordial black hole merger rate at high redshift universe. Okay. What about the lower mass end? So before I go there, is there any question from me at this stage? Whatever you're going to do at the higher mass end for the from the stochastic gravitational background data, yeah. It depends on the mass spectrum of the PBHs. Right now, not much, because our data is all over the place. But this is the mass scale. So if I make it heavier, it goes outside the band, it becomes difficult to detect. If it becomes too light, it again goes outside the band because of the overlap reduction function. So something around 10 to 30, 40, 50 solar mass, if there's a characteristics mass around that scale, we can do it a better job. I am not making a statement that I can detect individual masses. It is a distribution, probability distribution of the mass distribution with a characteristic mass scale MC. Right. But now I want to come to the lower mass end. Exactly, the MC value much lower. If I now ask the question, what about the lower mass end, which is a unique probe to primordial gravitational waves? This is the plot you are seeing as a merger rates. This is the star formation rate. This is the primordial black hole merger rates. And these are the horizons up to which we can detect individual event from third generation detectors like Cosmic Explorer and Einstein telescope for different masses. Means anything outside this will be stochastic. Anything outside this will be stochastic, and so on. Which means that if I want to measure whether there exists primordial black holes of 0.1 solar mass going through this particular distribution, this entire curve will be contributing to the stochastic gravitational wave background. So what's the measurability? Again, then all nearby heavy sources are detected, so they don't contribute to your background. Your background is now typically something of the order 10 to minus 13, 10 to minus 12-ish for different masses of the primordial black holes. So you can now see, in the previous plot I have shown you primordial black holes of 30-ish solar mass characteristic mass scale. Now these are of much lower masses. These are of the order 0.05, 1-ish and lower. So the key signature is again the same, it's a tilt in the power spectrum, but there remains a problem, right? Whether I make a lot of black holes of heavier masses or a lot of black holes of lighter masses, I do not know. I cannot break this degeneracy by just seeing this plot. It's just a single spectrum plot. Here you are seeing the forecast from Cosmic Explorer Einstein telescope. It's the work done by Matthew Minima, where you have shown that what fraction of primordial black holes?
So I have a question.
Yeah.
In the previous slide, you talked about the characteristic mass of the primordial black holes of 1 solar mass with an abundance 1. Now this abundance is the normal way of
No, this is the abundance of primordial black holes with respect to astrophysical.
Astrophysical black holes. Okay, that's what I want.
Fraction is the important factor is there is a fudge factor there. When I want to calculate the amount of primordial black holes mergers, there can be clustering. There can be a suppression factor. I do not know any of these factors. All I can care about that I have seen n number of black holes in the universe. What fraction of them follow star formation rate? What fraction of them don't follow? So this is the overall normalization I can only deal with in a observationally sensible way. And that ratio is captured by FPBH. Okay. So FPBH over FABH is 1.
Okay. Also, another question I had. So you talked about that the MC is the characteristic mass of the primordial black hole of a probability distribution.
Probability distribution.
So what kind of probability distribution?
Log normal distribution.
Log normal distribution.
Okay, great. So this is the forecast. What you start seeing it now, that in third generation detectors with the stochastic gravitational wave background measurements, we can actually go to the very low mass end, and we can ask whether there are primordial black holes which follows this increasing merger rate at high redshift or not, with a very high statistical significance. These are done for different combinations of Cosmic Explorer and Einstein telescope. I will not go to I will not read those. You can see those in my slides later. But the main take-home message is we will be able to make a statement whether this number is 1 or not, or 0. We can measure this make a statement from third generation detectors in the lower mass center. Now I'm going to change the gear and I'm asked the question that I have only talked about stochastic gravitational background power spectrum, but is it at all a sufficient statistics? Is it a quantity that I do and I'm very happy with it? How many of you think that can be the case? Because I told you it's only a shape, left, right, top, bottom. That's all you can do, nothing more. But if you can think physically, I think there is something more to it, right? So let's ask this question. If I show you these two plots and I ask, one of them has a time reversed, can you tell which one of them is that? Can any one of you tell me left or right in which one the time is reversed? Possibly you may not be able to do that because this is a Gaussian noise which is stationary, symmetric. It obeys a simple time symmetry. I go left or I right, I just don't know, I cannot distinguish it. It looks statistically similar. Is it going to be the case for gravitational wave signal? Can a gravitational wave signal has an arrow of time? The answer is yes. Things fall, things don't go apart. Two black holes comes nearby. As a function of time, two objects comes nearby, they start emitting more gravitational wave with higher frequency and so on. It doesn't go the outer way, right? So now if I ask the same question, if I see only a small phase where they look almost continuous like gravitational wave, frequency is not changing, they again look time symmetric. But if I now actually make the real case where the stochastic gravitational wave background is coming from black holes which is seeing the LIGO-Virgo-Kagra range, they are coalescing, they are falling in. Amount of energy and amount of energy that deposit at a lower frequency is very, very correlated with the amount of energy that emit at higher frequency because of the fall of them in the time. And this is what is shown by my PhD student Mohanty, showing by using a simulation that this very basic fact that the gravitational wave background will start breaking the time translation symmetry will lead to correlation between different frequency modes of gravitational waves. So far I was talking about omega GW, which is a autocorrelation, but something very interesting starts happening. If I start breaking time symmetry from the physics background, I start seeing generating this kind of distribution in the covariance matrix of the omega GW background. It's a new additional information, and you cannot produce this by just noise. So what it means, let's see, and this particular distribution depends upon whether black holes are heavier or black holes are lighter. An important aspect to understand that if black holes are of lighter masses, they exhibit correlation up to higher frequencies because they, first of all, they emit up to higher frequencies, and you now start generating correlations maybe up to from 50 Hertz to 30 Hertz, 20 Hertz, and all those frequencies. Whereas if I go to 70, 80 solar mass, my corresponding correlation starts changing. It moves to a bit of higher frequency ends, as you can see over here. And that's an additional, completely new physics-driven approach for us to discover the underlying mass distribution. If more objects at higher masses, are there at higher redshift, you expect to see a different frequency correlation of the covariance matrix than from the one which is lighter masses. Yeah. Yes, that will also happen there too if there are different length scales involved. That's right. That's correct. Sizes of different bubbles will live to a time dependent stochastic background.
I mean, in order to really see this effect, you would need to measure the correlations, which means you would need to measure phases. And in most of the analysis, you always start on the level of the power spectrum.
Right.
Because otherwise, the analysis has too many free parameters and it's a mess, no?
That's right. So you cannot measure them in phase. So what you basically calculate is that with respect to the noise covariance, do I have additional power in the different frequency bands? What you have to understand is that what is noise practically, I'll take a few, suppose what is basically noise tells me that suppose I observe something at 20 Hertz, at 21 Hertz is random, at 22 Hertz is again a random quantity. But if you have a gravitational wave of any physics origin reason, 20 Hertz and 21 Hertz is going to have a correlated power. So with respect to how much power is deposited at individual bands, they will show a correlation. So you have to draw the correlation on the power spectrum. It's a 4-point function.
But if at any time you see like not just one event, but 4, 5, 10 events.
4 or 5 candidates?
Yeah, I mean, if you see many events at the same time, then this will be more complicated, no? I think
this is the exact thing which is shown over here. So how many I see in individual bins? What is important is that there are 2 time scales. I couldn't talk about it here much. Sorry, 3 time scales. One is time scale over which the signal is varying. That is defined by the mass.
Right.
Time scale over which signal repeats at the time scale of merger rate. The time scale over which I observe the signal. That is my observation period time scale. Observation period time scale is much larger than the merger rate time scale, and the individual signals time scale is shorter, milliseconds, few tens of milliseconds, few hundreds of milliseconds. So this will not work for LISA, and this will definitely not work for PTA because they look more continuous. But if the signal is shorter, as shorter you go, more spiky or more structure you will get in the covariance matrix.
I see.
That's so the main place where this becomes useful, it starts becoming very different from inflationary stochastic gravitational background. It is not going to be showing you this particular feature. The covariance matrix is going to be diagonal, and we have possibly a room for doing something interesting. Yes. So maybe because we are taking questions in between, I'll go up to 45 minutes.
Yeah, so I think this was mentioned in the first talk also, that when calculating this correlation, you're taking some mass of the primordial black holes. But in the real scenario, it can be that there are different mass scales of the PBIs. So in that case, can you infer anything from the background?
Very good, excellent, that's right. Because what really depends, this is the ensemble quantity. This is not a one quantity. This is the ensemble average distribution of black hole masses at high redshift. That's why it's not a kinky feature, it's a summation or addition of many kinky features weighted by their population integrated in its redshift. So that's why you get a distribution of the correlation function. So this is for primordial black hole, this is for astrophysical black hole. In simple word, this is a power law mass distribution, this is a log normal mass distribution, and they start showing you very different features. But not a single object. You are basically asking what question? That if I take a 1-year data, and I break them into typically 192 seconds, and I now start calculating the covariance matrix between these individual bins, do I see a correlation between different frequency bins or not? And it's coming just from the fact that there is an arrow of time for the physics and not for the noise, which is correlated between different detectors. We have also done an analysis by taking correlated noise, which shows you more structures around the diagonal, but not far away from the diagonal part. Thank you. Are there any more questions? So what happens? What's the final outcome for doing all of this? The final outcome is that if I now start talking about only power spectrum measurement, I possibly get only this violet area curve on mass distribution, pair instability mass distribution, or delay time distribution. But as soon as I start combining the covariance matrix, now it is not only the shape of the power spectrum, but the covariance matrix structure, it starts breaking the degeneracy between the mass distribution and the merger rate. Means I can tell now whether I have more black holes of heavier masses at high redshift or not. And this particular what is showing you is that we make a very significant improvement in the data analysis when we take into account the covariance matrix. And work on this on the data is currently in progress. Though I have a plot, but I do not want to show it because of the time. I can discuss with you later. It's all done by Mohit. Okay, so now I'm going to switch to gear. What I told you right now, that with the LIGO-Virgo-Kagra stochastic gravitational wave background, detection or non-detection will lead to a very important understanding on the high redshift universe of a high redshift universe, which will give us a strong hint of whether astrophysical black holes or primordial black holes are there or not, and what are their typical abundances. Even if there is no primordial black holes, astrophysical black holes itself is completely unknown to us at high redshift universe. So it is going to definitely open a very interesting discovery space with the help of LVK, stochastic gravitational background analysis. Is there anything more you would like to ask me on this before I move on? I have a little bit time left. So now I'm going to switch gear to the higher mass end or lower frequency end, and I'm going to talk about what about the high redshift universe of nanohertz. And this is super interesting because now you start asking the question about how these small black holes I see in LIGO and this heavy black hole I see in nanohertz possibly, then evidence around 3 to 4 sigma, depends upon which you are talking about, where are they coming from? So how these heavy black holes are coming from, and what are their corresponding redshift distribution? This is a very challenging problem which practically cannot be solved analytically under any approximation. Why? Is there anybody can tell me that I have written an analytical simple model for galactic physics? The answer is no, it's a very complicated astrophysical problem. Supermassive black holes that sits at the center of these extremely complicated galaxies, and how they merge and how they grow is an extremely complicated scenario. And for that we need what we call as some kind of simulations. A simulation which is high resolution enough to see these black holes up to high cosmic time. In this particular frontier, this is a snapshot from a very high resolution simulation called Romulus, which can have like a 25 co-moving megaparsec box cube, which can see up to 0.7 kiloparsecs, or can actually see black hole masses of seed something like 10⁶ solar mass. Okay. That means I can now use a simulation suite to understand the growth and evolution of black holes, which can contribute to the nanohertz signal, which is completely different situation from the analytical calculation of the merger rates I can get from there. So this is the plot of the astrophysical stochastic gravitational wave background as a characteristic strain as a function of frequency. There are a couple of different effects. So first of all, there was a question yesterday about dynamical friction and this last parsec problem. What's important to understand is that these black holes are not sitting at an empty region. There are a lot of gas, there are a lot of baryonic matter around them. So when they come from a kiloparsec scale to a subparsec scale to emit in the nanohertz gravitational wave, they spend a lot of cosmic time and they lose a lot of energy by interacting with the environment. So if the environmental, this is our model where we have captured these environmental effects. So more stronger the environmental effect, more gas density, depending upon the properties we have identified from a simulation, this will come down, means less energy is emitted in gravitational waves. How long it is there, how long or until what time this effect is important, that gets imprinted on the frequency of the gravitational wave. So if it lasts long, the peak will be shifted towards right. And this is a very key signature which we should be able to measure from the data. Data is not going to show you this straight line, or otherwise you are going to be a real confusion, because how these black holes are coming nearby, it isn't going to be agreeing with our understanding of black hole growth. Another very important aspect, so this is the work done by Vida. She just finished her PhD on this particular topic. She's from Canada, working with us on understanding the nanohertz gravitational wave signal and their corresponding host properties. What's important to understand is black hole needs to grow. For anything to grow, it needs time. So your amount of time they spend means they are going to be mostly at a lower ratio. So here you are seeing a plot of masses of the host galaxies of those binary black holes, which are contributing to a stochastic gravitational wave background, the corresponding chirp mass of the black holes, and redshift in different colors, as you can see, and the sizes basically shows you in what typical ranges they are lying, low mass or high mass. So most sources which are heavier, that contributes to maximal to the stochastic gravitational wave background in the nanohertz range, are typically hosted by these galaxies which are pretty heavy in their stellar mass. They need to grow in their stellar mass. And this is a very interesting correlation we have seen from our simulations, yet to be confirmed from any observations. And that's the place where next frontier of correlation between black hole properties and galaxy properties are going to be playing a major role, because black holes plays a very interesting role in the ecosystem of growth of galaxies in the universe through feedbacks, and many of you know about this. But the problem now is that what we see in the stochastic gravitational wave background is at the largest scales. It's a very large scale signal of a stochastic gravitational wave background. We cannot detect very high resolution gravitational wave background currently. But the physics which drives the effect is coming from the coalescing of two black holes which are at the sub-parsec scale. The physics of sub-parsec scale gets imprinted on the largest cosmological scale depending upon how black holes in the universe are growing. There is a scale problem, right? I am talking about gigaparsec scale observation from sub-parsec scale physics. And this is a frontier which Mohit has again developed a new technique, an adaptive technique in collaboration, where we have with the team people from the Romulus team, where on one side we have mice-cat simulations, where we identify the growth of structures with cosmic time, growth of galaxies with cosmic time. Those scales are compared with the simulation box scales of 25 megaparsec to understand the underlying environmental of galaxies. And you put them under the underlying distribution of this adaptive technique of sub-parsec scale physics. And when you do all this, you start making a prediction, getting a result of the omega GW background and anisotropy from a completely physics-driven black hole formation history and galaxy formation history. What's very important to understand, the number of black holes which are merging at lower frequencies are much more in number, maybe a few, close to a few 100,000, and over here it's much tinier, like of the order of tens to hundreds. Or in other words, signal, if I have more gravitational wave sources on the sky, signal looks more isotropic. So the angular power spectrum of gravitational wave is low. But as I move towards higher frequencies, I have only a very few sources. Sky starts becoming extremely anisotropic. A key signature, very few supermassive black holes present possibly very nearby will drive the observation at higher frequencies and vice versa at the lower frequencies. And this will again generate what I call as the spectral spatial correlation. We have shown it very first time, these aspects, that it will be clearly observable quantities that is imprinted depending upon how galaxies and black holes are forming. I'll move on. I do not have much time, but what I now want to tell you that this last statement I made is that I have only a very few black holes in comparison to the number of galaxies, because the occupation fraction is not very large, which means if I see a sky, there are going to be only a few hotspots of gravitational wave background. They are not going to be like cosmic microwave background. They are not a field, they are more like a few sources. If so, whatever else you can call it, you cannot call it a Gaussian distribution. It is going to be an extremely non-Gaussian, extremely non-isotropic distribution of the stochastic gravitational wave background. So, very well-known quantity which is always measured until date as you speak, the angular power spectrum for the nano-hertz gravitational wave signal is definitely not the right thing to do, because it's only a summary statistics when the underlying distribution is Gaussian. We cannot do that, and a simple way to show that is that any Fourier mode you take, angular modes, the distributions of CLS are extremely non-Gaussian. This is coming from simulations at different frequencies. Do you know how to read these plots? They're like violin plots. They're the distributions obtained from 1000 simulations. And they show you a very, very different distribution. So what to do? How do we measure the stochastic gravitational background fluctuation if they are so anisotropic where Gaussian approximations completely fails? So now connected to the previous part I told you where to look for these supermassive black holes in the sky. They are possibly forming in the very heavy galaxies. They are forming where I have AGNs. I possibly have a quasar, or in other words, I have a tracer of supermassive black holes in the universe, which I can observe from galaxy surveys. What you are seeing here, if I take a galaxy distribution map and I identify all those places or positions on the sky where I have more galaxies or more AGNs in comparison to the blue one where they are less, and identify those positions in the omega GW background, and I define a new quantity, a stacked correlation, what we call as the multi-tracer stacking. In this approach, doesn't matter is Gaussian or non-Gaussian, I'm going to capture the same physics. I never tell about the underlying statistics. I add everything. Wherever there is less signal, there is going to be noise. Noise is going to add up to 0. Signal is going to build up, and you're going to see this signal directly as a tracer of anisotropic or isotropic stochastic background. It's again done from 1000 simulations showing us that if universe is isotropic, when I do a stacked correlation with a tracer like AGN, I will be seeing something very, very close to 0. This is for noise realizations. This is for what they call the cosmic variance or the different distributions of gravitational sources. But if it is anisotropic, it will show you a large signals. I think I do not have any more time. All I can tell you that this is a very promising window. So we are currently here about 64 pulsars. As we move with more pulsars, this avenue is going to give us a definitive measurement of stochastic gravitational background fluctuation on the sky, even if the distribution is completely non-Gaussian. I do not have time to talk about this, so ask me later if you want to know how cosmic evolution of supermassive black holes we can trace. But I will end my talk saying that this is really an exciting time, that we have so many different bands available to us and so many different also other probes like galaxy surface available to us. And synergies in these areas will be very key for both LIGO, Virgo, Kagra and nano-hertz gravitational wave signal. And we are part of all these different bands observations from extremely high frequency to CMBS4 observations from low frequency. We cover all these different collaborations, and my group members are working on these areas. So with this, I just want to say that this particular plane of mass and cosmic time is going to open up a major discovery space in the very near term future in both nano-hertz and hecto-hertz. Thank you so much.
Thank you for the interesting talk, Suvodip. We can take, I think, 2-3 questions now.
Sorry for taking more time.
No, it's okay.
And thank you for the nice talk. So I have one very simple curiosity. So when you talk about astrophysical black holes and primordial black holes, maybe for the case of primordial black holes, if they're formed in very early universe, have you thought about if there could be some impact of dark matter or WIMP or some dresses of dark matter, and whether that can also impact
the stochastic background kind of?
Yeah.
See, if there is enough amount of mass accreted, so if that shield you're talking about, they are mass comparable to the black hole mass, then they will show you as a signal. But that's not the case. Your amount of mass shell you accrete by any kind of scalar field or dark matter tracing is not going to be of the order of the black hole mass itself. So you do not going to get a lot of signal out, but you may get a lot of signal from the individual events. Are completely different story. They'll be absolutely great if these two black holes, some kind of dressing comes nearby, I can see some very interesting signal. But as long as the amount of growth in that, let's call it some shell, is not significantly in mass, our background will be not very dominated. Background's main issue is about how many sources and individual masses. So even if some of them are very heavier, if they're fewer in number, they will compensate each other.
But perhaps there could be some primordial features in the background.
Oh yes, that's true. I didn't even talk about those. If there's any feature in the power spectrum, any kinky structure, that's great. That we can definitely measure. We can start distinguishing that from the astrophysical one by this, either by using both omega GW and also this covariance matrix.
Yeah, so how do you use this to test GR, general relativity, this stochastic gravitational wave backgrounds? Can this be used to test gravity?
So ideally, I would like to use test cosmology, test fundamental physics with those quantities which are very solid on the astrophysical ground. I have individual events. which I measure in amplitude and in phase. If I really want to do testing GR, why should I throw those good events with SNR above 8, above 10? Stochastic gravitational background will not be a great tracer of seeing or testing gravity because it's a averaged quantity. Unless you pick up like features, which Anish was mentioning, some very specific property which you see in the frequency dependence, that you can capture. But any such effect from an individual event will be much better. See, combining maybe n number of events, I get an SNR of 5. But individual events I have an SNR of 8, 10 and so. They are much more informative for me to do physics on the fundamental physics side or on the cosmology side. Because fundamental physics, cosmology are common to everything. So I should use my best sources to do cosmology and fundamental physics. These things which I cannot measure individually, there is the place where you will win by looking at the stochastic diagram. That's my high redshift universe. That's my primordial black holes at high redshift universe. Make sense?
Yes.
Thanks.
All right, that's the question we can keep for the coffee break. And before moving to the next talk, let's thank the Suvodip again.